Okay, okay, so we're going to start this week's ROCKE-3D seminar with Tomas Fauchez from Goddard Space Flight Center. He's going to tell us about what I think looked like a really interesting paper on stellar models and how they also limit exoplanet atmosphere studies in emission. So take it away, Tomas.
Thank you, Mike. Yeah, thank you for having me today. And yeah, it seems that every time we are using models, but we have limitation, and so that has to happen as well for the infrared. And so that's an idea that Kevin Stevenson and I had like almost 2 years ago, I think, when it was the HW meeting back to Baltimore, and we were first skeptical about the original photometric observation of TRAPPIST-1b or C, when we have 12.8 and 15 micron measurement, and the first 12.8 measurement was really high in terms of flux, much higher than expected. And that triggered a lot of question. And it seemed that it was a calibration issue for that first out of 5 transit at 12.8. But it still had the benefit of starting discussion about assumption in terms of models at the value stage of using secondary eclipse data to get some exoplanet properties. And then back to so we tried this as cycle 3, cycle 4 JWST proposal to say we need mid-infrared spectra. We didn't get them because the TAC was saying it was not groundbreaking science. Yes, it's not groundbreaking science, but it's just making sure that the science we already have is not messed up by the models. But nevertheless, the team at MIT, Benjamin Rackham and Jean DeWitt, were like, okay, guys, you need to put that quickly as a letter, because that could be helpful for the 500-hour Rocky Worlds DDT program that is going to look at many of those targeted secondary eclipse. And they were calling for ancillary data that the community can put together for those observations, and this fit that pretty well. And we have also, of course, Benjamin Rackham has been known to be one of the experts of the TLS effect in the transit, where you are contaminated by the variability of the star. And Elsa Ducrot, also in Paris, she has been one of the lead experts on the TRAPPIST-1 system observation. So we built that team and came out in a quick paper in a few weeks on that. So it's currently in review in APGL. And so, of course, my favorite system, as you know, TRAPPIST-1b and C here are the targets that are the best for secondary eclipse measurement, because it's something that, you look at the thermal infrared radiation. So you want a planet that is hot. If you start to go in the habitable zone or beyond, it's much more challenging in terms of signal to noise ratio and the overall strength of the signal. But for TRAPPIST-1b and C, it's a very appropriate technique. And so the way the secondary eclipse works is like, well, because we cannot resolve the star and the planet, most of the time what we get is the flux of the star and the flux of the planet all together. And of course, the flux of the star strongly dominates the sun here. But once your planet passes behind the star, you only have the flux of the star. And therefore, you can now just simply derive the contribution of the planet that is missing. And so you get this absolute measurement of the flux of the planet and the flux of the star. And if you basically take that and as a wavelength dependent, you get what you have on the bottom left here, which is what we call the contrast, or the ratio between the flux of the planet and the flux of the star, usually in ppm, and which is also wavelength dependent. So until that point, we do not need a spectrum in a mid-infrared at all. No, synthetic spectra or an observed one, we don't need that. We have the absolute measurement in broadband photometry. The mid-infrared spectra become necessary when we try to interpret these contrast ratio, and we try to see, okay, what would be the planet's property that we will match this measured ratio. So that's why we need to combine that to a spectrum of the star. And we can play with different albedo for the planet. And of course, we have some degeneracies because the metallicity of the star is going also to affect the results, the log G of the star, and all these things. And so that's really at the stage of interpreting what the contrast ratio means that we need to rely on a spectrum. And so those are the paper that came out on the TRAPPIST-1 secondary eclipse measurement by Tom Green and here Ziba, both in 2023. And as you can see, we see here the eclipse depth, or FP over FS, also called planet to star flux ratio. And you can see that we have those measured data points. On the left, there are those black square with so relatively large error bars. The horizontal one is just because we do broadband, so we really don't do spectroscopy. It's a very large range of wavelengths. And vertically here, well, despite having 5 eclipse each of them, we still have something around 90 ppm precision and 1 sigma. That's the vertical error bar there. And so even if you fix one unique stellar model and you take a sort of ground truth for your star, you then have to start to guess what surface properties your planet can have, and then that will give you different eclipse depth as a function of the albedo you would expect from their surfaces. So first of all, we already have a problem there because all those fancy type of surface we have very, very, I mean, it's not super well constrained, specifically around that kind of star with a very red light. And so I think it's already a big stretch sometimes when we sort of try to use those surface model and apply them there. On the right as well, you can see very same thing. They compare to what could expect from a cloudy Venus or different kind of rock and composition. And with this kind of error bar, it's very hard to tell which model it would be most favored. So we have a big problem still in a secondary eclipse. The advantage, I would say, by comparison to transmission spectroscopy, if it's transmission spectroscopy, if you don't have an atmosphere, you have no data. You have a flat line, which is completely boring. And in secondary eclipse, if you have no atmosphere, you can still do characterization on the surface, which is quite interesting. But again, then we need to make sure that the model we use are appropriate both for the star and the surfaces of the planet itself. And so for the star, well, TRAPPIST-1 is a very small star, so it had a lot of advantages, but also being so far into the M dwarf, we are in M8, we are very, very non-black body. As you can see here, we have different stellar model, Kourous, that's the one we use in PSG. We have Phoenix, BT Settle model that are often used in GCMs, right, and Sphinx. And even if they have different spectral resolution here, it's not too important. And they are all normalized in a J-band, like done in the Green et al. Paper and Ziba. You can see that we are very far from the black body green curve. And so far, actually, that in the Ziba paper at 15 micron, where we get most of our secondary eclipse measurement, the absolute flux that they observed, which has usually a 1% precision, a little bit more, if you translate this flux into brightness temperature, you obtain a brightness temperature that is 30% lower than the effective temperature of the star. 30% is huge. It really means that we are very far from a black body, and we should definitely not use that assumption when we try to do science with TRAPPIST-1. And so, first of all, even if we know we should not use black body, I think it's been known that for a while, we still have a lack of model precision, as you can see here on this plot. So what we observe is, what we see here is the flux of the star, the top left corner, as a function of the wavelengths for, again, the black body as a reference, and then the 3 different models that are usually used, so Kourous, Phoenix, and Sphinx. And they are all being more or less to the same resolving power here, and you see noticeable differences between them. So that's the precision that we are lacking here for those models. And so when we try to do after is like, okay, let's now compute the eclipse depth, the contrast ratio between the planet and the star, fixing the flux of the planet the same across all the cases, but let's have the flux of the star being provided by one of the 3 models. And at the end, that will give us the difference that we have due to the choice of the stellar model when we derive the contrast ratio. And you can see that if you compare, so here I'm missing a U for Kourous, but if you compare Kourous and Sphinx, you have a difference of 80 ppm in your eclipse depth if you have used Kourous or Sphinx to predict your eclipse depth. 80 ppm is quite huge. And if you compare Phoenix and Sphinx, that are probably the two most used models here, they still have a 40 ppm differences between them. And that's the problem, because we have also derived that if we want to retrieve the planet albedo with a 0.1 precision on the albedo, we need a 29 ppm 1 sigma precision. And so even that, at just one stage of the model precision, we are already beyond what we need to do good science. So that's an issue. And if we compare to earlier type star, like a K5, for instance, we can see that the models are in much better agreement. We don't have Sphinx anymore, that is really an M dwarf model. But you can see that between Kourous and Phoenix, the agreement is pretty good and much closer from a black body. So we know that the earlier type star, they may have less absorption feature than M dwarf, but they still should have some. And we were like wondering here is like, we may see this very good model agreement for K star and even G star. We didn't plot it there, but probably because we have just a lack of opacity data for the star that have not been measured. Because before doing that science with Exoplanet in secondary eclipse in the mid-infrared, there was no need for the scientific community to get a mid-infrared spectrum of the star. There was no science cases out of that. So we are really wondering if the problem that we see here for secondary eclipse and M dwarf may be more general to any kind of star where mid-infrared spectrum have never been observed, and we all assume that should be close to a black body, while it may not be. And so beyond the precision problem that we have between the models, we have also a model accuracy issue. So here on this figure, we had the spectra that we observed with James Webb with NIRIS and NIRSpec, spanning from about 0.6, 0.8 micron to 5.3. And we can find, like, except in some region where we are partially saturated, which is always a problem, we fit very well the model spectrum. But once we get into the mid-infrared part, there are photometric data points that have been observed at 12.8 and 50 micron are significantly lower than the model spectra. Even here, if we have seen roughly 2600, it doesn't change much. But we have basically, we have an overestimation if we use Sphinx of 7% of the flux at 15 micron, and by 13% if we use Phoenix. In other words, if you want to have those blue and purple spectra here passing by the data point, you need to reduce them by 7 and 13%. And so there are a couple of questions that can go there. So it seems that if we have derived now quite accurately the effective temperature of the star at 2569 Kelvin. If we use that effective temperature, we can nicely fit the visible and near infrared, but not anymore the mid-infrared part. It's almost like we will need a second fit at a lower effective temperature to fit the mid-infrared. So that can be due that there are some absorbing space heat over there in the mid-infrared, maybe CO, maybe some clouds in the star that overall may decrease the flux in that region. Or we got unlucky and the flux decrease was localized to 12.8 or 15 micron, but I doubt that. They may just overall decrease of the flux. If we get a mid-infrared spectrum of the star, if we will observe it, that would be very interesting to compare that spectrum to the photometric data point. Because in a best case scenario, the spectrum should pass by the photometric data point. If they don't, there will be a couple of explanations for that. Mid-infrared variability that has now sort of been expected with the phase curve measurement we got for TRAPPIST-1b and C. So we actually advocate to, if we get a mid-infrared spectrum, to get one at 3 different epochs. So the star is having a rotation period of 3.3 days. So we can have like one every day, for instance, and see if it's varying a lot or not. If the variability is quite moderate and the spectrum still does not pass by the data point in photometry, that may be a sign of calibration problem for the photometry that we can only highlight and know if we compare those photometric data point with some spectra. So we really try to say that precision problem and accuracy problem could be solved by just acquiring a mid-infrared spectrum. And so this figure that we put in a paper done by Elsa Ducrot in Paris really show the whole mess that it is right now to try to interpret those data, because as I mentioned earlier, the vertical error bar are already 90 ppm. And then we have to deal with uncertainty on the potential log G of the star and metallicity, and then various kind of surface albedo. And on top of that, if we use a Sphinx model here in blue or Phoenix, we have a different result. And here Elsa has corrected Sphinx to try to match the fluxes over all of those data points. So we had to do empirical correction, which is quite risky. So we believe that if we first remove this problem of which stellar model do we use, we at least remove that uncertainty, and then we have to just deal more with the uncertainty on the surface properties of the planet, and just having a shorter error bar that can be just done by acquiring more secondary eclipse. And so when we put together this JWST proposal for a single observation, so we were able to say that we will only need 2.56 hours to get everything we need in terms of a stellar model in a mid-infrared. That will give us here roughly a signal-to-noise ratio of 80 at 15 micron for the star spectrum, which will be good enough, to be strongly used and as a ground truth kind of for then the secondary eclipse measurement. And we push that for MIRI MRS that has a resolving power that is higher in the order of a few fathoms, because we want to make sure that we resolve enough any spectral lines that the star can have in this mid-infrared region. So MIRI MRS, because of the higher resolution, is more expensive than LRS, the low resolution spectroscopy. But we are worried that if we use the cheaper LRS, we may just blend a lot of absorption line that we want to figure out, and then that would just defeat the problem that we have. So we really believe that is an ancillary data that may be really needed for any secondary eclipse observation, and that's really cheap to get. And so we already try to push that. And so I'm already to my conclusion in perspective, because it was short. It was a short letter, like we were limited to 4 or 5 figures. And so to summarize, there is no mid-infrared spectrum that has been acquired for M dwarf yet. We have determined that we will need 29 ppm precision to be able to distinguish between planetary albedo with a 0.1 precision step, and that the stellar model precision itself is already worse than the 29 ppm that is needed. But also that the precision is not the accuracy. We also show that even if we would have taken the median spectrum between the stellar spectrum model, we will still be around 10 to 15% off by comparison to the photometric data point. So there is these two things, the model precision and the model accuracy problem. And so therefore, relying solely on broadband photometry can be risky. What again, if we have calibration issues in the whole pipeline, if it's never benchmarked with a spectrum, we will never know. Also, I didn't mention here, but it's a bit a pity when we get, already a spectrum of the star from 0.6 to 5.3. Why not continuing and having the full spectrum of the star up to 28 microns with MIRI. That will really, for such a system like TRAPPIST-1, it is really a fantastic laboratory for comparative planetology. I think we can afford a 2.5 hour or something to get the full spectrum. Yeah, as I mentioned, what if we get this spectrum that do not pass by the photometric data point? As I mentioned as well, we may want to acquire such spectrum at 3 different epochs to test the potential variability in the mid-infrared. Again, like 2 years ago or so, everybody thought that the mid-infrared, there was no variability at all. We actually got our proposal rejected in cycle 3 because of that, because we were asking to test the mid-infrared variability, and the referee said that it was not going to happen. And then a few months after, we got 15 micron flare in our observation of the phase curve of TRAPPIST-1B and C. So c'est la vie. But yeah, I think we definitely need to test that. And I said it would be very cheap to acquire 1 spectrum. And so if you want 3, you just multiply by that. It's still, within 10 hours, it's quite good. And so because right now we have the 500-hour Rocky World DDT in a different kind of program, we really, with this paper, the idea was to advocate to systematically acquiring that as along every secondary eclipse observation. Like now, like also a few years ago, people, didn't take into account the TLS effect. Now that is very well known. Everybody now need ancillary data to take into account this TLS effect. We sort of argue that this issue we have with mid-infrared spectra is a sort of new TLS but for the mid-infrared. And so yeah, the 500-hour Rocky World DDT, and yeah, that's it. That was the end of my presentation, and we have plenty of time for questions, so please bombard me with questions.
Great. Thank you, Thomas.
Thank you.
So, any questions, anybody?
I have a question.
Questions? Yes.
Thomas, do you talk about maybe some known sources of uncertainties in these stellar models in the paper?
Well, yeah, that's the line list that they have. So they really try to be, as much up to date with Hightron, Hightom, and a different kind of line list. But nevertheless, they don't necessarily use all the same. And even those line lists, they just may be missing species that we will only know if we acquire the mid-infrared spectrum there. And so that's also one of the big difference we have with Kourous. So we put Kourous because it's again, it was a test that we have in PSG, but Kourous is 2005, so it's been 20 years old. So in 20 years, we have strongly, improved Hightron and Hightom in a different opacity data. And so that's not, when you compare to Kourous, it sort of makes sense that the differences is much higher. But nevertheless, when you compare Sphinx and Phoenix, they are supposed to be very up to date right now, and they still show differences because they don't have exactly the same opacity data.
So that was my same question. Is it just the line list and data that they're using, or are there other assumptions in these models that differ?
To my knowledge, is really mostly that line list data, and of course, after where do you cut different lines and all this, all the things that goes into the radiative transfer computation can be also an issue behind. I try to recall there was a paper specifically dedicated to compare Phoenix and Sphinx, like it came on like I think 2 years ago or so. Really go into diving into the details of the differences between the model. I need to come back on that paper. So yeah, it's there are the source of the opacity data is one thing, but there is also the way the data are binned down or not is also a crucial factor. Actually, on a different subject, so both in the Malbec intercomparison and also in a SAG 26 Rhino that is posed with everything happening, but is led by Ren Yu and Ty Robinson, we found that everything we try to simulate, if we get the line by line, the way we bin the data has a massive impact at the end on the simulation of the spectra. So I suspect as well that between Sphinx and Phoenix, there is the different binning also could play a role.
So Tomas, since the mid-infrared is so poorly characterized temporally, I mean, it seems to me 3 observations within a day of the star is probably completely insufficient. I mean, it's a start, but you don't even know how variable it is. Like you said,
Yeah.
it sounds like it's even worse than you're portraying, and that really you probably need simultaneous observations in these bands when you make the broadband observations. Because if the variability is highly variable, then you're going to still get garbage in and
Exactly.
garbage out. Yeah.
No, you're right. I think thank you for pointing that out, because it was actually a slightly difference of language between our proposal and the paper. In the proposal, because we were asking for observation time, at first we said, hey, we need to test the variability. So we want 3 epochs within one rotation of the star. The star rotates every 3.3 days. So for that, we wanted to see the variability. But inside the paper and everything we advocate for, we indeed say that we need this ancillary data systematically when we observe the star in secondary eclipse. So you're right, it just needs to be at the same moment, roughly, because if it's taken at a different epoch, that may be quite different. But again, if we would have obtained some James Webb data, maybe we may have been very surprised. Maybe we have 3 different epochs would be very similar, and then therefore the message can change slightly, where you say, okay, maybe you can use a median spectrum for your own data, or maybe if they are so different, then we're like, okay, yeah, you need to acquire that systematically at every secondary eclipse observations.
Yeah, you could be fooled. I mean, it's quiescent for the 3 times you took it, and then every time else it's just gone mad.
Yeah, absolutely. And we try to say this is, of course, we use TRAPPIST-1 because we've got tons of data and very, a sort of extreme case. But the DDT of 500 hours, which is huge, is really looking to different stars. Some are M3, some are M5. And we actually already got some feedback because Kevin Stevenson is part of the 500 DDT. So he discussed about this paper with them. And they were asking us to make a new figure, doing an M2 star and an M5 star, the figure that I'm showing right there, and showing the same thing to see if the difference is as bad for M2, M5. I think it would be better, but again, this will be still only the precision problem of the model. That will not help us to know where the accuracy of the model is with respect to the photometric observation, but yeah.
I can ask a non-astronomer question. Or go ahead, Mike.
No, go ahead, Nancy. Go ahead. I'll ask my question.
Okay, I just can you explain how do these molecular line lists opacity, how do they get updated?
That's so basically they are updated from lab measurement. When people like in different lab, like here with Erica, for instance, Erica Kohler, once you measure, we are going to try to push something for collision-induced absorption right now, for instance. So once we have that, the paper is peer-reviewed, then validated, then we are in touch with Hytron, Yuri, Gordon, and then you have to follow a certain protocol. And once it's validated, then it's part of the future release of Hytron or different models. So it's a step-by-step process. But so maybe with your question, maybe the opacity data now for the mid-infrared part of the star may have already been acquired in the lab, but have not been through the whole pipeline to go through those Phoenix and Sphinx model, for instance.
And so what were they using before they attained those data? They just interpolating, or there's some kind of parameterization?
Yeah, both. I mean,
Okay.
if none of that works, then after it's just like you assume black body in some part, because then you don't have any. If you don't have an absorber, you get into the black body mode. So, which is what which is what we have here for the K-dwarf. As you can see, if you go beyond 6.5 micron, here is really, really smooth. And so if you see the difference in ppm is really ultra tiny, so maybe just like we have no opacity data over there.
Huh. Wow. So what are are there like campaigns to try to fill in the blanks? Then how is there like who supports that kind of work? It's just NASA or other NSF? Who I'm just curious.
So right now we are not sure. That's the problem. So we put that together to say like we need to do that. I know that people. So at Exoplanet back here, we are in touch with some people doing combustion work, and so they have access to high temperature, and they are trying to find different cases where they can apply their data. And so I think different labs across the world that have different applications would just be in the right temperature regime to have those data, and then we have to know if those absorbing species make sense to have in a star, because you can do some combustion thing in a lab, but that would not make sense to have them in a star. So then we need to do some extra work into that. But yeah.
Okay, and I guess it's not really a coordinated effort. It's like each lab kind of picks something.
Yeah.
Interesting. Okay.
Yeah, usually,
Okay.
I mean, most of the time, at least for those are really into science, not industry, is really, it needs to be science driven. So if there is like right now we have it's a very specific science question to answer that will motivate that. But yeah.
Now you do. We were looking for life. Okay. Thank you.
Yeah, thank you.
So Tomas, one really quick question. So certainly Spitzer made observations of M dwarfs in the infrared. So you said there were no observations, but they must have been made. And also there's all these people that do this brown dwarf work, that they must have certainly made some observations of these stars in the mid-infrared over the last few decades. Is that not the case?
Yeah, but not a full spectrum like coverage. Like even Spitzer is sort of like broadband photometry, right, in different channels. And the problem is that with the noise that we used to get from Spitzer and the fact that it's not fully covering a spectrum, it's not enough to identify the absorber there. That's why we need the mid-infrared with MRS MIRI at like a resolving power of 3000 or so, because then we can resolve the absorption line. Otherwise, everything is blended, and we just see on Spitzer a flux decrease, but like we don't know if it's due to calibration issue, if it's an actual effect.
Okay.
But for brown dwarf, I did.
So there's no temporal data for the Spitzer stuff.
No.
Okay.
Not to my knowledge, but yeah, it's the really spectrum is like that we're seeing here going 5 even. So we propose MIRI MRS goes to 28 microns. So the coverage from 5 to 28 do not exist, at least for 5 stars. I don't know about brown dwarf, but again, that will need to look at what science could be done in a mid-infrared for brown dwarf. That's always the thing, right? That's what's before why it was never observed for M stars, because there was no science before that to motivate that. So.
Okay, any other questions in the room? Okay, I guess not. Oh, wait, Rory has a question. Go ahead, Rory. Sorry.
Yeah, hey Tomas.
Rory.
Great stuff. Really appreciate all the work you've done here. I guess I have a question sort of about the role of other planets in some of these systems, especially when you're thinking about trying to get that, sort of following up on Mike's point too about the variability of the spectrum. I mean, I imagine as planets are going around, you're getting different phases, and they're going to maybe contaminate the spectrum at this sort of level. I don't think you included any of that in here, and maybe that's because it doesn't matter. So I guess I'm just wondering, when you have these multiple planet systems, do you have to worry about that too much, or is that
not?
I think you do, but I don't know how.
Yeah, not too much. I mean, it will really depend on if we focus on TRAPPIST-1b, 1c is already colder, and we really have like a ratio of 1,000 by comparison to the emission of the star. And so we really swamp within the noise that we already have. So that's the thing. The contribution of the other planet exists in the total flux that we get from the system, but the contribution of each individual planet is completely swamped within the uncertainty we already have from the measurement. Okay. So if we will have an infinite precision, yes, we will definitely have to take into account that. But unfortunately, within even the 1% precision we have now in terms of the measurement of the absolute flux, the contribution of the other planet are more in the range of 0.01% or so. So yeah.
Yeah, great, thank you.
Yeah, sure. Good question.
Okay. Well, if there's no more questions, then let's thank Tomas again for a great talk.
Thank you very much.
Thank you so much, Tomas, for the short notice. And Good luck.
Thank you for having me. Yeah, thank you.
All right.